Assalamu alaikum everyone. So we'll continue our discussion on leveling, and so we'll do a quick numerical before we move to more complicated computations. So in this first question, we have to find out reduced level of a number of points, and the reduced level of the first point, which is the benchmark one, is given to us, and the reduced level of that point is 100. And then we will proceed further and the other points will keep showing up and we'll try to find out their elevation, and we'll try to solve this question by using the height of instrument method. So in order to find out the height of instrument of in our first setting, so what we have studied before as well is that in the reduced level of the benchmark, you add whatever reading you get on the leveling staff once your instrument is leveled, and that reading added up in the elevation or reduced level of the benchmark becomes height of your instrument. So this line over here, this plane, which is imaginary, has a reduced level of 100 plus 12.64. So 112.64 is the height of the instrument. So when we put all these values in the table, so we have the point whose reduced level we want to find out, and we have backside, foresight, height of the instrument, and elevation. There could be intersight as well, but we don't have that in this question. So we calculated the height of the instrument in the first setting, that was 112.64, and that was also our backside. The first reading taken in any instrument setting, 12.64, so that becomes your backside. Now elevation of the first point is given, that is 100. So the reduced level of the first point is 100. So now we have the next point, which is called as turning point 1. So that means that after this reading, we will change the location of our instrument. So the reading that we took on this position, on this leveling staff, which is the foresight, because we are only taking two readings in this instrument setting, the backside and the foresight. Now the foresight is taken at TP1, so we write it over here, 3.11. And in order to find out the reduced level of this point, what we do is that from the same instrument setting, since the height of the instrument remains the same, from the height of the instrument that we had calculated, 112.64, we subtract the foresight, and that gives us the reduced level of the next point. So subtracting 3.11 from the height of the instrument, you get 109.53, which is reduced level of TP1. Now TP1 can become our benchmark. Taking our instrument further, the next reading after setting up the instrument at a new position is taken at TP1, which was our new benchmark, and the reduced level of TP1 was 109.53. Now, in order to find out the new height of the instrument in the new location, you add the reading of backside on the same point in the reduced level of the benchmark TP1. So 109.53 plus 10.88. So that becomes 120.41, your new height of the instrument. Now that we have that, we can find out reduced level of the next point, which is TP2. So from the height of the instrument, which is in the second setting, 120.41, you subtract the foresight, 2.56, and you get the reduced level of the third point, which is 117.85. Similarly, a new point is introduced. We repeat the same procedure so that we reach this point BM2, whose reduced level is 124.47. Now, once you have filled out this table correctly, there is a check that we can apply, and the check is that the summation of the backsides minus the summation of the foresights, that difference is basically the difference in reduced level between the first point, our initial point, and our last point. So the difference between summation of backsides and foresights is 24.47, and which is actually the difference between the reduced level of our last point and reduced level of our first point. So once you're done with the computations, you are done with the calculations, you can apply this check to see if the calculations that you have performed are correct or not. So now we have a couple of definitions that we have already discussed, so I'll skip this slide. Now, in this question, they have again asked us to find out the reduced levels of the points TP1 and TP2. So, just a quick recap, they have given us the reduced level of the benchmark 356.68. In that, you add the backside 1.27, that becomes your height of the instrument. From that reduced level of the height of the instrument, you subtract the foresight, and that will give you reduced level of the point TP1. And similar procedure we will use for the point TP2. So some mistakes that should be avoided while doing this process. Uh, the most basic one is reading the staff wrong. So that's why I have emphasized on reading the staff correctly a lot, and I have given you a lot of videos to watch on that. The second mistake is moving the turning point. Use a well-defined turning point. So that's very important because to find your TP becomes the new benchmark. And if your benchmark is wrong, that means all the work that you will do after that will be wrong. So whenever you set out a benchmark, it has to be done very accurately, and the point has to be very distinct in the ground. And then we have mistakes with extended rod. Make sure that the leveling rod is fully extended so that when the person who is reading the off the leveling staff does not commit any mistake. And then we have some other ones that we have discussed as well, level rod not vertical. So if the person holding the leveling staff does not hold it vertically, if it sways forward or backwards, that means the reading that the person of the telescope will read will be more than the actual reading. So the reading is minimum when the staff is truly vertical. Settling of leveling rod that happens when the legs of the tripod stand are not anchored firmly into the ground, because once you anchor them, after that you level the instrument. But if you don't anchor them and level the instrument, they might settle into the ground a little, and that will disturb your leveling, your the horizontal plane of the line of collimation, and that would mean the reading you would take would be wrong. So then we have some other errors like environment, wind, and heat. We'll see how they cause an error. So some suggestions for good leveling: anchor the tripod legs firmly so that there is no settlement. Check the bubble level before and after every reading. So since wind and settlement can disturb the leveling of the instrument, so you need to check that the circular bubble is in the center after a couple of readings, so just to make sure. Take as little time as possible between backside and foresight so that the two readings are taken in the same conditions. Try to keep the distance between the backside and the foresight equal. So that is actually how you avoid an error, and we'll talk about it in just a while. So some methods of performing leveling calculations. So one method that we have discussed a lot was height of the instrument. So I hope you are familiar with that by now. And the second one is called as rise and fall method. So rise and fall method is even simpler. So I can explain it on this diagram. So let's say I don't want to calculate the height of the instrument, right? And I want to proceed with the rise and fall method. So basically what that means is the rise and fall method tells you about how much is the elevation difference between two consecutive points. Either the second point is above the first point or it is below the first point. So that is called as the rise and fall method. So in this case, what we do is the benchmark is given, its reduced level is 356.68, and then we take the reading of the first staff on which is on the benchmark and on the second staff which is on the point whose reduced level we want to find out. So the difference between the two give you rise or fall between the 2 points. So in this case, every time what you need to do is you need to subtract foresight from the backside. So in this case, when you subtract 4.91 from 1.27, that would mean that you're getting a negative answer. So that means there is a fall. The second point is below the first point. Alternatively, if backside was 4.91 and the foresight was 1.27, then the difference would be positive. That means that the second point is above the first point. And that is consistent with what we discussed, that lower the point, more the reading on the staff. Higher the point, lesser the reading on the staff. So the difference between the two gives you rise or fall. In this case, we get a fall. And whatever the difference is, 1.27 minus 4.91, you subtract it from the benchmark reduced level, 356.68, and you would get reduced level of this point TP1, which will be smaller than 356.68. Now that we have reduced level of this point, this becomes our benchmark. In the new setting of the instrument, again, backside minus foresight, again, the answer is negative. That means there is a fall. So whatever the difference is, subtract that from the reduced level of TP1 and you get reduced level of TP2. So this is how the rise and fall method works. It's pretty much simpler than even the height of instrument method, and you can use either one in performing calculations. So that doesn't matter. So talking again about some errors in leveling. So first we have the very basic one, instrumental errors. So that is when you have a parallax or the crosshairs are not exactly horizontal because you read the staff reading using the help of crosshairs. So those are two perpendicular lines in your telescope in your view that mark the center point of your vision. So rod not correct length, tripod legs loose. So all of these are instrumental errors. And then we have the line of sight or collimation error that I wanted to discuss. So this error is that when you level your instrument, your that means that the line of collimation or the line of sight is completely horizontal. That means this line is tangent to the level surface or the level curve. But if due to some error in the instrument, and after that, while your instrument is telling you that the instrument is leveled, the circular bubble is in the center, but even then, your line of sight might be at an angle. It might not be horizontal. So that error in your instrument or in that line of sight, that angular error is called as collimation error. And once you have that, that means the correct reading to be read is this one, but you're actually reading either a bigger reading or a lower reading depending on what sort of error is there in your line of collimation. Even if there is error in your instrument, you can avoid this error by placing your instrument midway between the 2 points whose elevation difference you want. Why? Because if the instrument is midway, then it means that whatever error you are reading over here, the same error would be in your second reading. And what we are doing in the end is taking the difference of these two readings. So the error cancels out. But if your instrument is not in the midway, that means one error would be more and the other one would be smaller. So the errors won't be cancelled out and your final calculation would have an error. So as much as possible, if the work that you need to do isn't too much, it is advised that your instrument should be placed midway between the 2 points whose elevation difference you want to find out. And the sole reason of doing that is to get rid of the collimation error. Then we have some natural errors, error due to Earth's curvature and error due to refraction. So, like I told you in the very first lecture of leveling, that the level surface is curved. That is because the surface of the Earth is in curvature. So, if you are noting down a reading in which your instrument is placed at a far distance from the leveling rod, then it means the effect of the curvature would be more. And the effect of the curvature is determined by this equation where EC is the error. This is the horizontal line or the level line when your instrument is leveled, and this is the level surface. And remember what we talked about, that your horizontal line or horizontal plane is at tangent to the level surface, and the level surface is the one which is at equal elevation from the earth, which is also in curvature. So while you should be reading this value, what you actually get is a bigger value due to effect of curvature of the earth. So this error is equal to s square over 2r, where s is the distance between your instrument and the leveling rod, and r is the radius of curvature of earth. So for 100 meters, if the distance between the instrument and the leveling rod is 100 meters, this error is almost 1 millimeter. So usually we can neglect this, but if you're doing some work in which you precision is utmost precision is required, then you can always compensate for this error using this equation just by calculating the distance between your instrument and the leveling rod. The refraction error is because of variable density of Earth's atmosphere. So that means the light that you are catching gets diffracted in the air. We get the same error when we are working with lasers and other sorts of electromagnetic energy. So this is a natural error. It reduces at different times of the day. So during the night time, this error is the smallest. So if you can use some instruments at night time, then it means this error would be minimum. But usually we ignore this error because the value is not too much. Then some temperature variations can cause the leveling rods to expand, but again, we can neglect this error. Strong winds can cause both the instruments to vibrate, so that can affect the readings a lot, and it is advised to wait for a little bit and then continue with the work. Then we have settlement of the instrument. We discussed this. This can disturb the levelness of your instrument, and if you don't re-level it, that means the reading you would take would be different. Or if you are taking multiple readings using the same setting of the instrument, if the instrument keeps on settling in the ground, uh, your line of collimation would keep on changing, and then all the readings that you take would be meaningless. Then we have some personal errors. You don't remove the parallax, or the bubble is not centered until you keep on taking the readings. So we have a couple of them. Then talking about types of leveling operations, so we already talked about simple leveling and differential leveling. So simple leveling was the one in which we place the instrument midway between the 2 points whose elevation difference is required. And differential leveling was when we make the instrument take up different positions and we take a number of readings. Then we have two new terms, fly leveling and check leveling. Fly leveling is when you want to connect benchmark starting point of your project. So, like we discussed, that permanent benchmarks are the ones which are set up by the government, and they might not be close to your project site. So, sometimes you want to connect the benchmark to your project site, or even at your project, the reference point that you want to take is far away from the place where you want to do the work, and you want to shift the benchmark. That means you want to find out reduced level of some point on your project so that you can proceed further on. So in that case, what we do is we place our auto level at such a location that we can see as far as possible, so that we don't have to change the location of our instrument again and again, because we don't need intersites. We don't need reduced level of points between the benchmark and starting point of our project. So we just need to shift the benchmark or find a reduced level of some point on our project site. So in that case, we only take backside and foresight, no intersights, and we place the instrument in such a way that there are no obstacles and we can see as far as possible. So we can get over with this as soon as possible. And then we have check leveling. So imagine you are working on a closed traverse A, B, C, D, and point A is your benchmark, and its reduced level is 100. Using that, you perform leveling and you find out reduced level of point B, C, D, which were unknown, right? So the job is done, but just to make sure that the work you did was correct, now that you have the reduced level of the point D, you can find out reduced level of point A, which is known already, but once again. And if the reduced level of point A comes out to be similar to what it was before, 100, that means all the work you did midway for the point B, point C, and point D is correct. If the reduced level of point A comes out to be different, that means you did some error. So check leveling is done when you connect the last point in your work to the first point, so that you can check if the first point gives you back the same reduced level that it should. So it gives you an indication of that the work that you did is actually correct. So this method is not just reduced for closed traverse, you can also do it for open traverse or any service key. Then we have longitudinal and profile leveling. We actually talked about this. So it is the operation of taking levels along the center line of an alignment. So basically you do this when you want to construct roads or railway tracks or water supply pipelines, sewerage pipelines. So whenever you have a linear project or a project that goes in the linear direction and it has pretty significant distance. So in that case, you want to build profile of the land, and the image that you see over here is actually a sectional view of the center line of the road. and correspondingly the ground topography. So this is how the ground is changing, and you get this on the y-axis we have elevation or the reduced level, and on the x-axis we have stations. So stations mean after a constant distance, you keep on finding out levels in a straight line, and then you draw the whole profile. So this is the land profile, this is a sectional view, and then you can decide what should be the elevation of your road and what should be the slope of the road. And you decide the elevation of the road in such a way that the amount of soil that you have to excavate is equal to the amount of soil that you have to fill up. So that really economizes the project. So this process is called as longitudinal or profile leveling. Okay, so one last question before we move to some lengthy questions. So in this problem, what you have to do is that they have given you benchmark reduced level of this point, and you have to find out reduced level of the point A, B, C, and the point D. And there is just one setting of the instrument. So you are not shifting the instrument. That means you don't have a change point or you do not have a turnover point. So with this setting, what we are going to do is we are going to use the rise and fall method that we just discussed. So as the benchmark is 100, the first reading is taken at the benchmark. So that is the backside, and it is 0.75. The second reading is taken at the point A, which is the interside, and it is 1.25. The difference between the backside and the interside is negative 0.5. That means there is a fall. So you will subtract 0.5 from 100. So that will give you reduced level of the point A, which is 99.5. Now we will forget about the first point. Now we have the reduced level of the point A, and this is our new benchmark. Now one reading on the same point, which is again 1.25, because we haven't shifted the instrument or have not changed its height. So that is 1.25. And on the point B, the reading is 2.75. So when you subtract, again, the answer is negative 1.5. That means there is a fall. And from the reduced level of the point A, 99.5, you subtract the fall and you get reduced level of the point B. Similarly, you move to the next point. The point B becomes your reference benchmark. One reading on that, 2.75, and the other reading on the point C, 1.5. So you subtract 1.5 from 2.75. Now you have a positive answer. That means there is a rise, which means the point C is above the point B, and you will add up this rise in the reduced level of the point B, which is 98. So 98 plus 1.25, now you have reduced level of the point C, and now this becomes your benchmark. So this is how we proceed with the rise and fall method. So we have one more example with the height of instrument method. So the solution is given, but you will try this on your own, and we'll discuss this in the class. So this is it